There is a very interesting case that we need to study here. Consider two molecules, both of them have polar covalent bonds in them. The first one is ammonia, where the dipoles would be pointing towards nitrogen. Another molecule, NF3, where the dipoles would be pointing towards fluorine. NH3 and NF3, both of them have polar covalent bonds. However, the resultant dipole, we might think NF3 must be having a higher resultant dipole moment. Why? Because NF bonds are more polar than NH bonds. Why? Because probably fluorine is more electronegative. So you might get that feeling that probably NF3 as a whole, right, would have a higher resultant dipole moment than NH3. Now, here we just try to understand the importance of orientation, which affects the resultant dipole moment of a molecule. In NH3, all the dipoles are oriented towards nitrogen. And you know that nitrogen, after making 3 bonds, will always have a lone pair of electrons. The bond moment of lone pair of electrons will always point in this direction, goes away from nitrogen. Now, if you consider the resultant bond moments, right, you find that the resultant of these 3, I told you, right, is given by, you have 3 polar bonds like this. The resultant will be given by somewhere from the center here, right? And therefore, you have the resultant dipole moment going like this. The direction would be in downward direction. These two dipoles, to a certain extent, cancel out each other. However, in this case, the resultant dipole goes in the direction of nitrogen. So if we consider the resultant dipole and the bond moment of this lone pair, right, they seem to have the same direction. Because they have the same direction, and dipole moment being a vector quantity, you find that the bond moments, they add up, and the resultant dipole moment would be a much higher value. So in spite of having less polar covalent bonds, NH3 as a whole, right, as a complete molecule, will have a much higher dipole moment than NF3. This is a very interesting case that you all have to know. The next we have is, something like, or the third category of the bond, which is the coordinate covalent bond. The coordinate covalent bond, uh, is generally formed in a little different way than a regular covalent bond. Not all covalent bonds are formed by, proportionate sharing of electrons, the two atoms between which a covalent bond gets formed. Each one of them generally will give 1 electron for sharing, and a covalent bond gets formed. This is a normal covalent bond. But at times, the formation is a little different. There are cases in which the two atoms which intend to make a covalent bond in between them, right, any one of them will give just an empty orbital, and the other atom will give a completely filled orbital. And there would be sharing between the two orbitals, one empty and one completely filled. And this would result into formation of a covalent bond. But this covalent bond is formed in a different way. And therefore it is called a coordinate covalent bond. A very, very simple example that we can study here is, you add an acid like HCl in water. Right? You add an an acid like HCl in water. What happens? You know that H plus ions which are liberated from HCl, they combine with water to form H3O plus ions. How is an H3O plus ion formed here? Very simple. You have water with two lone pairs of electrons on oxygen. When H plus comes across a molecule of water, you find that H plus doesn't have any electrons. It would just have an empty orbital, 1s orbital, right? Well, oxygen would have two bonding pairs of electrons around it and two lone pairs of electrons around it. These lone pairs, they are found in two different orbitals. Any one of these orbitals, which is completely filled with two lone pairs of electrons, right, is shared with the empty 1s orbital of H plus, which would result into formation of molecule or molecular ion like H3O plus. Here we find that one of the bonds is a coordinate covalent bond, and to distinguish it from rest of the covalent bonds, right, we always put an arrow here, right? So coordinate covalent bonds are generally shown by arrows pointing from donor towards the receiver. The same kind of bonding you observe in NH4, where NH3, right, has nitrogen with lone pair. When this NH3 comes across H plus from an acid, right, it would generate a coordinate covalent bond, and there would be overlapping between the completely filled orbital of nitrogen having lone pairs and 1s orbital, completely empty 1s orbital of nitrogen, and this would result in the formation of coordinate covalent bond. Even in molecules like BF3, where the octets are not completed, right, the central atom is deficient or it lacks electrons, and such molecules, right, can have empty orbitals in their valence shell. And if this is the case, then molecules like ammonia having lone pair of electrons would give lone pair of electrons to electron deficient central atoms like boron, and you have a coordinate covalent bond generated between the two. Right? The question is, how do we come to know whether a molecule has a coordinate covalent bond or not? Right? That part I would be talking about more in the part where I would be telling you about formal charges. So by evaluating the formal charges or by calculating the formal charges of different atoms in Lewis structures, right, one can get an idea about the existence of coordinate covalent bonds. This is one of the easiest ways of knowing whether a molecule has a coordinate covalent bond in it or not. Right? I can tell you. I can take one example. For example, you can take ozone. The Lewis structure of ozone is this. If you calculate the formal charges of different oxygens, you find that for this oxygen, the formal charge would be 6 minus lone pairs. So 4 non-bonding electrons, right? So 6 is the number of valence electrons in oxygen, isolated oxygen, minus number of non-bonding electrons, minus half the number of bonding electrons. Bonding electrons for this oxygen would be 4. This comes out to be 0. For this oxygen, right, you have 6 minus 2 minus half of 6. What would that be? This will be plus 1. So this is plus 1. And for this oxygen, it will be 6 minus, 6 minus half of 2. This will be minus 1. So this is minus 1. Now, when you come across Lewis structures in which the adjacent atoms have, the positive and negative charges, then it is very easy for you all to think that this oxygen, which is positive, might have given electrons for sharing to the empty orbital of this oxygen here. So this oxygen is at a net gain of 1 electron, and this oxygen is at a net loss of 1 electron, making this oxygen a +1 and this oxygen -1. So we may understand that there must be a coordinate covalent bond between these two oxygens, where this is the donor and this is the receiver. This is the best possible way of detecting the presence of coordinate covalent bonds in molecules.